So this will be our last lecture video of the semester. So we're going to skip a few things because we lost a little bit of time due to that extended spring break. So, so this will be the last topic that we talk about. And this is a typical type of application of basically thermodynamics, which involves the first law, and we're going to talk about the second law in terms of these objects. And these are called heat engines. Okay. We're also going to talk about refrigerators as well, but we're going to primarily focus on heat engines. So a refrigerator is basically just the opposite of a heat engine. But what does a heat engine do? So basically what a heat engine does is it tries to take disordered energy, basically from the gas due to the fact that there's kinetic energy and etc., and then tries to get something out of it, which is work. So basically what a heat engine does is it tries to take this idea of disordered energy and then use that to be able to do work. So let's talk about what a heat engine is. So basically what a heat engine is a cyclic process. My daughter stole my red. That little girl. All right, well anyways, we'll have to go with that red. So basically what a heat engine does is it takes from a reservoir. So in this case we have a hot source. And then down here we're going to have some sort of cold source. So this is a reservoir at a colder temperature. And then basically these two are going to be connected to each other, okay? So what this thing does is it basically tries to use the fact that, again, what we know is that heat flows from a hot source into a cold source. So here we're going to take energy from the flow of the heat from the hot and then try to use that to then get something out of it, which is then going to be work. And then whatever is left over, we're then going to dump into the cold source, so that we're going to have a heat cold flowing then into our cold reservoir. And then this is then going to be a cyclic process, because whatever is left in here is going to get heated up back into the hot source, and then we're going to pull that down. Okay? So basically, if you think about like your car, this is your radiator, right? Radiator has the cold source. That then gets brought through the engine due to combustion, which then heats it up, and then you use that combustion then to drive the pistons and the universal joint and the axle and all that stuff to basically get work out of it. So this is what we call a heat engine. Contrast that, we then have what's known as the refrigerator. So let's talk about a refrigerator. So a refrigerator basically is exactly the same idea. So again, we have a hot source. So this is at T hot. And then we have a cold source. So here then is my T cold. And again, this is going to be some sort of cyclic process. So these guys are actually going to connect to each other. So what this does is basically the opposite. So what it's trying to do then is what? Draw energy out of the cold source back into the hot source, right? So basically I'm trying to draw things out of the cold, put it then into the hot to then cool this thing down. Now, turns out that this is not a spontaneous process. So what we know is that heat spontaneously goes from the hot source to the cold source, but heat does not go from the cold spontaneously into the hot, okay? So this is what we call a non-spontaneous process. So to do this, to have this process actually happen, right, to get something to happen in here, we have to actually do the opposite. So instead of having our system do work, we have to do work onto our system, then to draw then heat out of the cold source. So now I'm trying to draw heat out of the cold, but I'm going to have some left over, and that some left over then is going to go back into the hot source. So this is then going to be Q hot, and then this thing is going to drive through a cyclic process. So basically what this means then is that a heat engine is any type of cyclic type process. So it means if I was drawing a PV diagram, so this is pressure then versus my volume, this is what my heat engine is going to look like. It's going to be some sort of cyclic process, meaning that if it starts here at A, it's going to run through that process and come back to the state of A. Right? Now, as we talked about when we talked about our different thermodynamic processes, since this starts off and finishes at A, that means it starts and finishes at exactly the same thermodynamic state, which means that the change in internal energy for the system then must be equal to 0. Okay. Now, since this is equal to 0, what that means then is that this must be equal to the heat flow plus the net work done on the gas, which means then that what? The net work done on the gas must then be equal to minus the heat flow. Right? Now, this is true. In this case, this is going to be the net heat flow. So this means the net work done on the gas must then be equal to the net heat flow through the system. Okay. So this is a heat engine and this is a refrigerator. Again, these are going to be cyclic processes. So again, I'm going to connect these two together to make sure that this thing happens in a cyclic fashion, which means my PV diagram, this then is going to be the net work, both by the gas and in the gas, or on the gas, I should say. So that the change in internal energy, again, the net change in internal energy, I should write, is equal to 0. Now that doesn't mean going from this state here, A, down to this state, B, that the change in internal energy is equal to 0, because it doesn't have to be. It just means that if I start here at A and I come all the way back to A for the cyclic process, then that internal energy change must be equal to 0. So good. So basically, from here, we can define what's known as the efficiency. So the efficiency, we're going to call this, I think we call that E. Yeah. So we're going to define the efficiency E. So the efficiency then is going to be defined then as the desired output divided by the desired input. So this is what we call the efficiency. Now in this case, our desired output is simply the work, right? We want to get work out of this thing. So in this case, we need work. Right? Our desired input is we want to take out from the hot, so we want to have heat flowing into the system. So our desired input is to only insert Q hot and then get work out of this. Right? But from here, what we can see then is that what? We have heat coming in, we have heat coming out, and what's left over is simply the work. So from here, we can then say that, well, the work is actually the same thing as what? Q hot minus Q cold, all divided by Q hot, which is then the same thing as 1 minus the ratio between Q cold and then Q hot. So this is what we call the efficiency. Now, what is never going to happen is that Q cold is never going to be equal to 0. We're never going to have no heat flowing out when we do this. We're always going to have to dump some heat back into the cold reservoir. So from this gives us the idea of what's known as the second law of thermodynamics. So originally, historically speaking, the second law of thermodynamics was developed this way, which is in terms of heat engines. So let's talk a little bit about the second law of thermodynamics. So the second law. So the second law of thermodynamics basically says is that heat spontaneously flows from T hot to T cold. Never from T cold to T hot. So this is our first definition of the second law. So the second law simply says, it defines what's known as a spontaneous process, which means that heat will spontaneously flow from T hot to T cold, but never go in the opposite direction. Okay? So in this case, this is what we call a spontaneous or irreversible process. So this is what's called an irreversible process. So irreversible means that it goes in one direction. It doesn't go both ways. So in this case, again, if this was my T hot and this was my T cold, so in this case, Q only flows in this direction, which means that this system only has activity in this direction. You'll never find it actually going in the opposite direction. So this is what we call an irreversible process. Now, other examples of irreversible processes are an egg breaks, but it never goes back together, right? This is an irreversible irreversible process, or if you bake a pizza, I can never unbake the pizza. This is another irreversible process. So this is one definition of the second law. Another definition of the second law is what? That no heat engine will ever be 100% efficient. Which means, again, if I look at the efficiency, which is going to be 1 minus Q cold divided by Q hot. So basically what will never be is that this ratio here will never be equal to 0. So this thing is always going to be less than 100% efficiency, because to get the efficiency, then I would multiply this by 100 to get the percentage. So here, with the efficiency was simply equal to 1, I would have a 100% efficient engine. So what the second law says, then, is that you can never have a heat engine which is fully 100% efficient, because I'm always going to have something dumped into the cold reservoir. So I always have a byproduct left over. I can never turn all of Q hot into directly work. That's impossible to do. Now, a question then arises, well, what is the most efficient that we can get? So meaning, if this thing can be never 100%, what is the then maximum amount of value at which this thing can actually occur? So to answer this, we have to look at a completely theoretical type of heat engine, which is what's known as the Carnot engine. So let's look at the Carnot engine. So what's a Carnot engine? So a Carnot engine is a completely theoretical device. So basically meaning that we can never actually build one of these in nature. Okay? So what that means then is if we calculate the efficiency of a Carnot engine, then any realistic engine that we create must then have an efficiency which is less than or equal to the Carnot engine. But again, since we can't actually build a Carnot engine, it then by default has to be less efficient than the Carnot engine. So what is the Carnot engine? So basically, a Carnot engine takes the heat engine through a fully reversible process. So what that means is, so again, an irreversible process is one which only goes in one direction. So again, heat only flows irreversibly from hot to cold. That's it. If I have something which has, say, friction in it, that's also an irreversible process. So again, as we talked about before, if I started with something, say, here, and I move it across here, and there was friction involved, if I move it back to the original position at which I started, I'll never have exactly the same amount of energy at which I started, because that's an irreversible process. I'm always losing energy because as I'm moving, I'm losing energy. As opposed to gravitational potential, where if I start off with this chalk, and I move it down, and I move it back up, well, now I've gained back the amount of energy at which I lost, right? So if I start off here and I go down here, I'm losing gravitational potential energy. But now if I come back to the original position, I have now gained all that energy back, which means that this is a reversible process. So if I go here and I come back, I restore the amount of energy at which I had. So a Carnot engine then is an engine which allows for this thing to be fully reversible, which basically means that it's ignoring things like friction or anything that's going to take energy away from the system, or basically cause it to be an irreversible process. So again, that's what makes this thing basically theoretical, because I can never actually build an engine which has zero friction and doesn't lose something somewhere and become a irreversible process. So good. So what does this thing do? So basically, we're going to have our two isothermal lines. So here is my first one. So this is going to be T hot. And I'm going to have a colder isotherm, say somewhere down here, where this is now going to be T cold. So what does the Carnot engine do? So basically, we're going to start off at some point A here. Okay, so this is my initial position. And then we're going to what? Expand the gas along this particular isotherm. So we're going to expand it along the hot isotherm to some final position of B. Right? So I'm expanding my gas here. Then, to bring it down to the cold isotherm, what we're going to do then is adiabatically keep expanding our gas, now from this particular position to some final position, let's call this point C here. Okay, so now we're going to adiabatically cause this guy to move in this direction. Right? Now, talk about some things that we know. So again, here, since this is an isotherm, we know the change in internal energy going from A to B then must be equal to 0, because this is along the same temperature. Okay. Which means we're going to have, what, by the first law, the heat flowing into the system going from A to B then is equal to minus the work done on the gas going from A to B. So basically what's going to happen here then is what? Since this is expanding, the work done on the gas will be negative, so this is going to be positive, which means we're going to have heat flowing into the system. So at this stage, we have heat flowing into our system. So this is then going to be QA to B. Now that we're at point C, what we're going to do is now we're going to compress our gas. So we're going to compress it along this particular isotherm to some other point. Let's call that point, say about here, which is then point D. Okay? So now I'm going to compress my gas along an isotherm along here, which again means that what? The change in internal energy going from C to D will also be equal to 0, which means that C to D will be equal to minus the work done on the gas going from C to D. But in this case, since the gas is compressing, that means we're doing work on the gas. So this is positive, which makes this guy negative, which means heat is going to flow out of the system. So here, we then have Q C to D, okay, which is going to flow out of the system. Finally, to make this thing a reversible process, or not reversible, but a cyclic process, we now have to, again, adiabatically compress it a little bit further, back up to the original point. So again, this is an adiabatic process, and this is also adiabatic. Now, so this is now a fully reversible process. I can go, and I've now reached exactly the same position that I was at before. I didn't lose any energy. There's no friction. There's no anything which is going on. So I have a fully reversible process. So this thing represents the most efficient engine that I can actually create. Now, also what's nice here is that what? According to this, we also know that what? For adiabat, the heat is equal to 0. So the heat there is also equal to the heat here, which are equal to 0. So the only heat flows I have into or out of my system are along these two isothermal processes. Now, the other thing I know is that for an isothermic process, the work is directly related to the temperature, which means that here, the heat going from A to B then is simply equal to the temperature, which is the hot temperature. And then here we have that the heat is then also equal to then the cold temperature. Right? So if I go back to the efficiency, so in this case we have that the Carnot efficiency is then equal to 1 minus Q cold divided by Q hot. But in this case, Q cold is the same thing as the work going from C to D, because that's when the heat is flowing out of the system. And that's simply equal to the cold temperature. And then Q hot is going to be when the heat is going into the system, which is then Q A to B, which is then directly related to the temperature T hot. So in this case, this is simply then going to be equal to 1 minus T cold divided by T hot. So this is what's known as the Carnot efficiency. So the Carnot efficiency, again, is the greatest amount of efficiency that a particular heat engine can have, because it only depends on the temperature of the hot reservoir and the temperature of the cold reservoir. Doesn't depend on anything else. Good. So that brings up then another definition of the second law of thermodynamics. So let's go back to our second law. So now this is our third interpretation of the second law of thermodynamics, where this one now says that what? The greatest efficiency of any heat engine operating between T hot and T cold is that of the Carnot engine. Oops. Spell. There we go. Then it goes on further to say then that the efficiency then of that engine between those two temperatures of T hot and T cold must then be less than the Carnot engine. So any engine operating between these two temperatures, between T hot and T cold, must have an efficiency less than the Carnot efficiency. So this is another statement of the second law. So the second law basically says, again, there are three now interpretations. One, heat spontaneously will go from a hot source to a cold source, but never from a cold source to a hot source. This defines, again, what a reversible versus irreversible process is. Second one says that, what? A heat engine will never be 100% efficient. We're always going to have some leftover Q cold. And then finally, the third one says that between two temperatures, so any heat engine working between two temperatures of T hot and T cold, the greatest amount of efficiency we can have is that of the Carnot efficiency. And therefore, any other heat engine must have an efficiency less than that of the Carnot efficiency. So, this is about as much as we can talk about with the second law. There are other definitions of second law when it comes to ideal gases and what the actual meaning of it is and all that good stuff. But again, we lost about 3 days, and we just can't get those days back. So we got to stop somewhere. So I guess we're going to stop here. So good. So having learned about this, let's now do an example. So here I have a monatomic gas which is taken through a cyclic process described by this plot that I'm going to draw. And we know that at one point the temperature is given as such. Okay, so let's draw our PV diagram. So here I have volume here in meters cubed. Here I have pressure in simply pascals. So this is going to start here at 2 meters cubed and here at 6 meters cubed. Starts here at 2 pascals and then ends at 8 pascals. So this point here is point A. This point here is point C. And then this point here is point B. So in this case, what's going to happen then is we're going to expand our gas along this line initially, going from A to B. Then we are going to decrease the pressure, but at constant volume here. So this is an isobolometric process going from B to C. And then finally, we're going to compress our gas along an isobaric process back to point A. Okay? And what we're told is the temperature at A, besides we know now the volume and the pressure at A, the temperature at A is also 290 Kelvin. Okay? So the things I want to know are, part A, what's the number of moles? So how many moles are inside of this gas? Part B, what I want to know is what is the temperature at B? Part C, what I want to know then is what is the work going from A to B, in this case. Part D, then what I want to know is what is the work going from B to C? That's part D. Part E, we want to know what is the work done going from C to A. So what's the work going from C to A? F is next. Then what is the net work done? So what is net work equal to? G is next. G, what is the change in internal energy going through the complete cycle? So what is my change in internal energy for the cycle? what's that guy equal to? Just wrote down the answer, but that's fine. H is next. What then is the heat added taken from the system during the complete cycle? Okay, so what then is the net heat? So this is what we want to know. I didn't ask anything about efficiency, so we can actually do efficiency if we want to then. But anyways, close enough. It's good enough. Now, first things first, definitely expect one of these on the exam. There's a couple on the practice exam. There's also one of the group exercises that I gave, actually 2 group exercises that I gave that basically involve all of this stuff. So the point is there'll be one of these on the exam. It'll be one of the long problems, so definitely make sure that you understand and know how to do these. So good. Let's look at a first. So here we're looking for the number of moles. Well, the easiest thing to do is use the ideal gas law at point A here because we know the pressure, we know the volume, and we also know the temperature. So from here, we can solve the number of moles then is just equal to the pressure at A times the volume at A divided by R times the temperature at A. Right? Plug in my numbers. What I get in this case then is the number of moles is simply equal to 0.0016. So that's my total number of moles. B, so good. So for part B, here since this satisfies, or this is an ideal gas, and this is in thermal equilibrium, and this is also in thermal equilibrium, in this case we know that up here this also has to satisfy the ideal gas law. So here we know the volume, we also know the pressure, we now know the number of moles, so we can also use the ideal gas law to solve for the temperature, or we can do what we did before, which is simply take the ratio of the ideal gas law at B divided by the ideal gas law at A, so that way we don't need to know the number of moles or the universal gas constant, and then just look at everything in terms of the ratios. So if we do that, we're going to get the pressure at B times the volume at B divided by the pressure at A times then the volume at A must then be equal to the pressure, or sorry, the temperature at B divided by the temperature at A. So from here, we just simply have to rearrange. So this is going to give me my temperature at B must be equal to the temperature at A times then the ratio of these things. Well, from here we know the pressure at B is simply 4 times the pressure at A. So this is simply going to be 4. And then from here we know the volume at B is 3 times the volume at A. So this is simply going to be 12 times the temperature at A. So plugging my numbers, what I get in this case then is 3,480 Kelvin. So that's a lot. So that's almost half of the surface temperature of the sun. So basically at this stage my heat engine would have melted, but let's not worry too much about that. These are just hypothetical numbers. Great. So good. So that's part B. So let's talk about part C. So part C, we know that, again, when I'm looking at a PV diagram, the work is simply the area under the curve. So in this case, we have 2 areas. We have the area of the triangle plus then the area of the rectangle. So this is going to be 1/2 the base, which in this case is going to be 4. Right, so 4 meters cubed times the height, which in this case is simply 6. So times 6 pascals plus the rectangle here. So that's going to be 4 meters cubed as well times then 2 pascals, which means the work going from there to there is going to be 20 joules. Right? Okay. Part D, the work going from B to C, well, that's just simply equal to 0 because that's an isovolumetric process. So there is no change in volume. So the work going from B to C must simply be equal to 0 joules. Great. The work going from C to A, well, that's just going to be this here. So just the rectangle, which is just this part, which is then simply equal to, so going from C to A, so that's going to be equal to -8 joules. There we go. Now, notice here I'm doing the work done by the gas, not the work done on the gas, so just be a little bit careful with that distinction. Good. So that means the net work done is simply going to be the sum of all 3 of these, so it's going to be 20 plus 0 minus 8, which is simply going to be equal to 12 joules. So that's our net work. Change in internal energy for the cycle, well, that has to be 0 because it's a cyclic process. So as long as I know it's a cyclic process, that has to simply be equal to 0. The net heat, well, we know the net heat by the first law says that 0 then is equal to the net heat minus the work done by the gas, net. And remember, in this case, I'm using the minus sign because these I calculated was the work done by the gas, not the work done on the gas. And remember, the work done on the gas is negative the work done by the gas. So this just tells me that the net heat must be equal to the net work, which is then simply equal to 12 joules. Okay. Now, in this case, if I also wanted to know, let's add an extra part, I. So the efficiency, well, the efficiency then is going to be equal to minus Q cold divided by Q hot. Okay. Now, to find those Q's, so basically from here, you would then have to find the change in internal energy going from here to here, and then find out what that Q is. Find the internal energy change going from here to here, using that the work is equal to 0. And then that's going to give you that work, or that Q, and then you're also going to find this Q. So in this case, Q cold, I'll let you guys calculate this, it should be equal to minus then Q going from C to A, divided by then Q from A to B. Please listen to loud music. So anyways, this should be some sort of percentage, so this will end up being something like 0.27 or something like that, which means it's 27% efficient. I haven't actually calculated, so I'm not quite sure. But again, this is something that you should expect to see, so something like those ones that I put on to practice, those that are in a group, or something like this, where I'm going to give you something which goes through some sort of complete cycle, and then from there you'll be asked to calculate a whole bunch of different things. Again, for each one of the individual processes, you'll just have to go through and calculate each individual thing. That's where most of the amount of points are going to come from, but they're pretty straightforward. So, if you want, we can do another example of this kind of later. But yeah, so that's it. So that's it for all the video lectures. So after this, I will make one more, which is just the review. We'll talk about that, and yeah. Otherwise, I'll again see you guys on, I think, Monday evening. So we'll talk a little bit about exam 5 and a little bit about the final, whatever questions you guys have. And then other than that, we're pretty much all set. So that's it.